At precisely 4:27 a.m., silence shattered across the Eastern Front. Not with artillery shells or missile strikes, but with something far more calculated, far more devastating. 240 autonomous drones lifted into the pre-dawn darkness, each one programmed with coordinates that would rewrite the rules of modern warfare in less than 3 hours. What happened next wasn't just an attack. It was a masterclass in strategic patience, technological precision, and the kind of tactical brilliance that military academies will study for decades. The sky held its breath as those machines began their journey. Each drone no larger than a briefcase, each costing less than a luxury car, yet collectively carrying enough destructive potential to cripple an entire supply network worth hundreds of millions. Ukraine had waited 73 days for this moment. 73 days of satellite reconnaissance, signal interception, and weather pattern analysis. 73 days of watching, learning, and preparing for a strike that would prove once again that in modern conflict, brains triumph over brawn every single time. But here's what makes this operation truly extraordinary. This wasn't random violence or desperate retaliation. Every single drone in that swarm had been assigned a specific target, a specific route, and a specific timing sequence calculated down to the millisecond. The planners knew that at 4:27 a.m., shift changes would create 90-second gaps in radar coverage. They knew that morning fog would reduce thermal sensor effectiveness by 34%. They knew that supply convoys followed the same predictable schedules they'd monitored for over 2 months. What they created wasn't just an attack formation. They engineered a symphony of destruction where every note played at exactly the right moment to achieve maximum impact with minimal resources. And the results would leave military strategists around the world asking one terrifying question. If a smaller nation could coordinate this level of precision with off-the-shelf technology, what does that mean for the future of warfare itself? The operation began not at dawn, but 3 weeks earlier in a converted warehouse outside Kyiv. Inside, technicians worked around the clock, modifying commercial drones with enhanced batteries, upgraded navigation systems, and payload compartments designed for maximum structural damage. Each unit underwent 47 individual tests before receiving operational clearance, flight stability at various altitudes, communications reliability under electronic jamming, explosive effectiveness against reinforced concrete and steel plating. But the real weapon wasn't the drones themselves. It was the intelligence network that fed them targets. Ukrainian cyber specialists had infiltrated maintenance schedules, supply manifests, and personnel rotation logs from facilities across a 200-kilometer front. They knew which buildings housed critical equipment, which storage depots contained the most valuable material, and which command centers coordinated defensive responses. More importantly, they understood human psychology. Military personnel develop routines, especially during extended deployments. Guard rotations happen at predictable intervals. Radio checks follow established protocols. Even alert levels fluctuate in patterns that careful observers can map and exploit. The drone swarm wasn't just attacking infrastructure. It was exploiting the comfortable predictability that develops in any long-term military operation. The launch sites themselves represented another layer of tactical innovation. Rather than using obvious military installations that satellites could easily identify, Ukrainian forces established 16 concealed positions in abandoned industrial complexes, unused agricultural buildings, and camouflaged forest clearings. Each site controlled between 12 and 18 drones, with launch times staggered to create maximum confusion among defensive systems. The beauty of this approach became clear when enemy radar operators tried to track the incoming threats. Instead of a concentrated formation approaching from a single direction, sensors detected scattered contacts appearing simultaneously across multiple sectors. Standard defensive doctrine calls for interceptor missiles to engage the largest concentrations first. But when targets are dispersed across such a wide area, traditional air defense systems face an impossible choice. Spread your interceptors thin and risk missing everything, or concentrate fire and watch smaller formations slip through uncontested. Ukrainian planners had studied this dilemma extensively. They calculated that existing air defense networks could engage roughly 60% of incoming drones under optimal conditions. But optimal conditions assume traditional attack patterns, clear weather, and defenders operating at peak readiness. None of those assumptions held true at 4:27 a.m. on a foggy morning when rotating shifts had created gaps in radar coverage. The psychological impact extended beyond immediate tactical confusion. Defensive forces had grown accustomed to dealing with larger, more expensive weapon systems. Cruise missiles, fighter jets, and ballistic projectiles that cost millions of dollars each and arrive with dramatic radar signatures that provide minutes of warning time. These drones appeared suddenly, moved unpredictably, and presented targets so small and numerous that traditional engagement protocols simply didn't apply. Even more unsettling was the realization that this technology was scalable. If 240 drones could overwhelm existing defenses, what would happen when that number doubled or tripled? Military procurement cycles take years to develop new countermeasures, but drone technology evolves in months. The strategic balance was shifting faster than institutional responses could adapt. The first targets became visible on thermal imagery at 5:43 a.m. Not the drones themselves, but the heat signatures of their initial impacts. Fuel storage facilities erupted in brilliant flashes that illuminated the morning mist. Ammunition depots followed in secondary explosions that shook windows 15 kilometers away. Command bunkers lost power as electrical substations sparked and died under precisely placed charges. But the most devastating strikes weren't the loudest ones. While dramatic explosions captured attention, other drones were methodically destroying communication relays, radar installations, and logistical coordination centers. The kind of unglamorous infrastructure that keeps military operations functioning but rarely makes headlines when it fails. Within 90 minutes, a defensive network that had taken months to establish was reduced to isolated pockets of resistance with no reliable way to communicate or coordinate responses. Supply lines that moved thousands of tons of equipment daily ground to a halt. Artillery batteries fell silent as ammunition resupply became impossible. An entire theater of operations began to collapse not through overwhelming force, but through surgical precision applied to critical vulnerabilities. The aftermath revealed something even more significant than tactical success. This operation demonstrated that asymmetric warfare had entered a new phase where technological innovation mattered more than numerical superiority or massive budgets. The economic mathematics were staggering. Each drone cost approximately $3,200 to build and deploy. The total operation required an investment of roughly $768,000. Yet the infrastructure damage exceeded $47 million within the first hour alone. When you factor in operational disruption, delayed supply chains, and the cascade effect of critical system failures, the actual cost to the defending forces approached $200 million. This represented a return on investment that traditional military strategists had never seen in conventional warfare. But numbers only tell part of the story. In underground command centers 400 kilometers away, defensive coordinators watched their screens fill with chaos they couldn't process fast enough. Standard engagement protocols assumed threats would follow predictable flight paths, maintain consistent altitudes, and present clear target signatures. These drones violated every assumption simultaneously. Flight patterns shifted every 30 seconds based on pre-programmed randomization algorithms. Altitude changes occurred so frequently that missile lock systems couldn't maintain target acquisition. Some drones flew barely 15 meters above ground level, using terrain masking to avoid radar detection. Others climbed to maximum service ceiling before diving toward targets in unpredictable spirals that made interception calculations impossible. The electronic warfare dimension added another layer of complexity that defensive systems simply couldn't handle. Rather than relying on GPS navigation that jamming could disrupt, these drones used visual terrain recognition software loaded with detailed topographical maps. Even when communication signals were blocked, each unit continued executing its mission based on landmark recognition and inertial guidance systems. More sophisticated was their counter-jamming capability. When defensive forces activated high-power electronic warfare systems, the drones didn't just resist interference. They adapted. Onboard processors analyzed jamming frequencies and automatically shifted to alternative communication bands. Some units even used the jamming signals themselves as navigation beacons, following electronic interference directly back to its source before striking the transmitter installations. The coordination between individual drones created emergent tactical behaviors that surprised even their operators. When lead units encountered stronger than expected air defenses, following drones automatically adjusted their approach vectors to exploit gaps in coverage. If one sector became too heavily defended, the swarm redistributed itself toward areas of lesser resistance without requiring human intervention. This adaptive behavior emerged from relatively simple programming rules, but the collective result was devastatingly effective. Like a flock of birds avoiding obstacles, the drone swarm flowed around defensive positions while maintaining overall mission coherence. Traditional military doctrine assumes that destroying command and control systems will disrupt coordinated attacks. But when each individual unit operates semi-autonomously, there's no central point of failure to target. The human factor proved equally decisive. Defensive personnel had trained extensively for conventional air threats, but their psychological conditioning wasn't prepared for swarm attacks. Fighter jets and missiles approach as discrete, identifiable targets that trained operators can engage systematically. A swarm presents dozens of simultaneous threats that overwhelm human decision-making capacity. Radar operators found themselves staring at screens filled with so many contacts that target prioritization became impossible. Which threats pose the greatest danger? Which could be safely ignored? How do you coordinate missile launches when new targets appear faster than existing ones can be engaged? Training exercises had never simulated this level of simultaneous threat density. Even more unsettling was the silence. Conventional attacks announced themselves with engine noise, radio chatter, and the distinctive signatures of high-performance military equipment. These drones approached with barely audible electric motors, no communications traffic, and thermal signatures so small they blended into background noise. The psychological impact of being attacked by nearly invisible, nearly silent machines proved profoundly disorienting. Air defense crews reported a phenomenon that military psychologists had never documented: target saturation anxiety, where the sheer number of simultaneous threats creates a freezing response rather than focused engagement. Operators knew they were under attack, but couldn't process the information quickly enough to mount effective resistance. The strategic implications extended far beyond this single operation. Military planners worldwide were forced to confront uncomfortable questions about existing defensive investments. Billion-dollar radar systems designed to detect stealth fighters struggled against $3,000 drones. Sophisticated missile interceptors worth $2 million each were being used against targets that cost less than a family car. More troubling was the scalability factor. This attack used 240 drones, but the technology could easily support 2,400 or even 24,000 units in a coordinated strike. Manufacturing costs would decrease with mass production, while defensive requirements would increase exponentially. The economic advantage would only grow more pronounced as drone technology became cheaper and more capable. Intelligence agencies began reassessing threat profiles across multiple theaters. If this level of coordination was possible with commercial components and open-source software, similar capabilities could emerge anywhere with sufficient technical expertise and modest funding. The barriers to entry for sophisticated military operations had dropped dramatically. fundamentally altering the strategic landscape. The operation's success also demonstrated how modern warfare was shifting toward information dominance rather than physical superiority. The months of surveillance, pattern analysis, and timing calculation proved more valuable than the drones themselves. Victory belonged to whichever side could collect, process, and act upon intelligence more effectively. But perhaps the most significant revelation was how quickly technological advantages could be developed and deployed. Traditional weapons systems require years of development, testing, and procurement. These drones were modified, tested, and operational within weeks. The cycle time between innovation and battlefield implementation had compressed to an unprecedented degree. This acceleration of military technology development suggested that future conflicts would be won by whichever side could adapt fastest to changing tactical requirements. The morning fog lifted to reveal a new reality. 240 drones had cost less than a single fighter jet, yet accomplished what entire squadrons couldn't. They proved that in tomorrow's conflicts, victory won't belong to whoever spends the most, but to whoever thinks the smartest. The age of asymmetric warfare just evolved, and the implications are only beginning to unfold.